morning students. Today I am going to start the first part of chapter 2, that is electrostatic potential. So in order to describe a electric field, we are going for electric field intensity term in our first chapter. But we can describe the electric field in terms of a scalar quantity also. So the electric field can be described by a vector quantity, that is the electric field intensity term. Then we can also describe the electric field in terms of a scalar quantity, that is electric potential. So electric field intensity gives us what is the force experienced per unit charge. So in order to know what is the force experienced by a charged particle in a region of electric field, we are going for electric field intensity. In order to find out what is the energy associated with a charged particle placed in an electric field, we are taking the term electric potential. So electric field intensity at a point actually gives us the force value experienced by the charged particle at that point, whereas electric potential term actually gives us an energy term. And this electric potential can be given by what is the work experienced by a charged particle. So this electric potential concept arises from the concept of potential energy. So in order to understand this electric potential, we will first understand what is electrostatic potential energy, what is the potential energy difference. Then we will proceed for the electric potential and we will derive the value for that, and we will see that is equal to the work done in bringing a unit charge from infinity to that point. So let us first start what is our electric potential energy difference. So in class 11th we know that whenever work is done against some force, that is stored as potential energy. Here also in case of electric force, we will see that whenever work is done against an electric force, that work will be stored up as potential energy at that point. So let us proceed for electrostatic potential energy difference. So electrostatic potential energy difference, that is the potential energy difference between two points. So suppose there is a positive Q charge placed here. Okay, due to this charge, we will have an electric field region here. So in this electric field region, if a charged particle is supposed to place, then due to its position, it will have some potential energy due to the interaction with electric field. So let us bring a charged particle, suppose a charged particle plus Q from point P to point R. So the charged particle is placed here and we are bringing a positive charged particle from point P to point R. So since we are bringing this from here to here and the force is repulsive force, we have to do some work against this repulsive force, and the work done against this repulsive force will be stored up as energy at this point, and that will be our electrostatic potential energy for this point. So suppose first this point P is at a distance of r1, and we are bringing this charged particle from point P to R, which is at a distance of r2. So what is the force? First we will see. Due to Coulombic force of repulsion, we will have a force formula, and that is F external. We have to do work against this repulsive force. So for that I am writing F external force. So F external force will be K Q1. So in place of Q1 I will write Q. In place of Q2 I will write small q. And what is the distance between them? The distance between them is r1 square. Then, but this external force must be equal and opposite to the electrostatic force. In order to place this particle against this repulsive force, we have to do some work, and that force should overcome this electrostatic force. So for that external force, must be equal to the electrostatic force, and if we will go for direction, so the value must be equal and opposite to the electrostatic force. So I can write that F external must be equal to minus of Fe. So now let us find out what is the work done in bringing the charge from point P to point R. So for that I will write what is the work done by the external force. So formula will be integration of F external dot dr. So dr means the small displacement. So in place of F external I can write, as I had discussed, minus of Fe d. So F external must be equal and opposite to electrostatic force. Again we know that Fe is equals to QE. Okay, and next, okay, we will put the limit. We are bringing the charge particle from P to R. So from P to R. So QEdR. In place of E, what is the electric field at this point? The electric field will be, according to formula, KQ by R square dr. So now I will take common this one, minus of KQQ and integration of 1 by R square dr. And since it is from P to R, that means for dr limit we will put R1 to R2. So R1 to R2. R1 to R2. So what is the integration of 1 by R square? The integration of 1 by R square will be minus of 1 by R from R1 to R2. Then this minus minus will be positive, and I will write that KQQ by 1 by R2 minus 1 by R1. This term I will write here. So W becomes equals to KQQ by R2 minus KQQ by R1. We are bringing from R1. So what is this KQQ by R2? This term I will write it as U for potential energy at R minus potential energy at P. So this term is our potential. So this one is for UR. We will define it as potential energy expression for point R. That is KQQ by R2, and UP is termed as KQQ by R1 for this point. So see, this work done is stored as changing potential energy. Whenever we will take this point P, first thing I will define what is your electrostatic potential energy. The potential energy difference, it is equal to the work done in bringing a charge particle from one point to another point. So electrostatic potential energy is defined as the work done in bringing a charge particle from one point to another point. Now I will discuss about potential energy. First I had written for potential energy difference. So in order to write potential, in order to describe potential energy, we will take this point P, or we will say that this point, this charge particle has been brought from infinity. So if we will brought this charge particle from infinity to this point, then this R1 becomes infinity. So I can write again that in order to define electrostatic potential energy at a point, W is equals to KQQ by R2 minus, in place of R1 I will write this is equal to infinity, because now we want to bring the charge particle from infinity to point R. So these terms become 0, and in place of R2 let us write, in place of R2 let us write R. That means the distance from here to here. Then we will write that W is equals to KQQ by R. And this work is stored as electrostatic potential energy at that point. So in order to define the electrostatic potential energy at a point, we will say that it is the work done in bringing the charge particle from infinity to that point. Again I will define the electrostatic potential energy at a point is defined as the work done in bringing the charge particle from infinity to that point. Then I will define what is electrostatic potential. Again, electrostatic potential is the potential energy per unit charge. That means how I will define the potential? I will say that potential, we will define it by a letter V. Electrostatic potential is the work done in bringing a unit charge from infinity to that point. That means we got this value. W is how much? Now K Q by R divided by Q. That means Q will be cancelled and the potential value will be your KQ by R. So if I will bring a unit charge, suppose +1, if +1 coulomb, if I am bringing a charge from infinity to that point, the work done by him is equal to the electrostatic potential. So let us now revise this portion, that what is the electrostatic potential energy difference? No, it is the work done in bringing a charged particle from one point to another point. What is electric potential energy? Now, electrostatic potential energy is defined as the work done in bringing a charged particle from infinity to that point. And whenever we are saying for a unit positive test charge, that is electrostatic potential. So what is electric potential? No, in order to bring a unit charge from infinity to that point, the work done is equals to electrostatic potential. Here we got for a charged particle, here we are getting for a unit test charge. So electrostatic potential is the work done in bringing a charged particle from infinity, bringing a unit positive charge particle from infinity to that point. So next class we will go for electrostatic potential due to a point charge, and we will derive that, and that will again come as KQ by R. How it is different from the electric field? In electric field term we are having an R square term, whereas in potential we will have a R